The Radix ledger consists of three fundamental components. First, a networked cluster of nodes. Second, a global ledger database distributed across the nodes. Third, an algorithm for generating a cryptographically secure record of events. An instance of Radix ledger is called a universe. The Radix ledger is a distributed database. It is designed to be horizontally scalable, supports semi-structured data, and can update entries. A local ledger instance operating on a node can be configured to store all, or part, of the global ledger. A subset of the global ledger is known as a shard. The total shard space is configurable per universe, but is immutable once deployed. Any event within the Radix universe, such as a message or transaction, is represented by an object called an atom. The Radix ledger stores all atoms that exist in a universe. Every atom consists of discrete objects or particles. Atoms are composed of particles, and particles occupy shards. Nodes and validators serve a set of the total shards. They can reconfigure to support any subset of the shard space, helping to ensure that the universe can handle large load requirements without requiring expensive hardware to operate a node. Sharding is a fundamental design feature of Radix, which implies a robust approach for guaranteeing that atoms are in the correct shards, and an efficient method for determining which nodes will retain copies of which atoms. If an atom consists of 3 particles, that atom touches 3 shards due to the particles within it. So there are at most 3 sets of nodes that will validate that atom. Each of those nodes also store a copy of the atom locally. If we know only one of the shards or particles that the atom uses, we are able to find and fetch the full atom. The more shards an atom touches, the more copies of it there will be in the network. An atom that is present in multiple shards increases the redundancy and availability of that atom. Atoms have some data too, but it's largely metadata, and they define the order of execution of the particles. The maximum number of particles in an atom, local copies, is limited to 1 million. All atoms contain at least one particle having endpoint destination, a receiver, represented by an endpoint address. This particle is called payload particle, serving as communication. The payload particle consists of encrypted data, participants, destination, signature. An example of a payload particle is a communication sent to one or more parties, like an email or an instant message. A message particle would have subject heading, any attachments, and the message itself as its data. Endpoint addresses are derived from an identity, such as a user's public key, and are used to route events through the network. Transfer particles are another types and are used to transfer the ownership of an item. The transfer particle consists of consumers and consumables, encrypted data, participants, destination, logic or script, signature. A transfer particle has data on the amount being transacted, the token, who are the receivers, and so on. The data that the particles carry are kinda like the arguments to a function, with the particle itself representing the function being called. While payload particles are relatively simple, comprising of some arbitrary data, destinations and a signature, transfer particles are more complex. Both types of particles are finite state machines, input, green, or output, red. A known item is represented by a transfer particle and its consumable. Ownership is defined as a sequence of transfer particles, which provide an auditable history of owners over time. To transfer ownership of an item, alpha, contained in a transfer particle in atom, alpha, to Bob, Alice creates a transfer particle which references her as the current owner and signs it with her identity. The transfer particle is given input state up, consumable, green, and is to be consumed, which will change the state to down, red. Alice also creates a new particle, beta, which contains the item, alpha, being transferred, along with the identity of the new owner, Bob. Both the transfer particle in atom, alpha, which references the current owner, and the new transfer particle which reference the new one are packed into a new atom and submitted to the network for verification. When verified particle, alpha, becomes consumed, state down, red, particle, beta, is set to up, created, green, and ownership is transferred from Alice to Bob. The consumed, red transfer particle can be used as a building block for a new atom. Some transfer operations may require that item, alpha, is not transferred to item, beta, in its entirety, such as currency. Transfer particles can be configured to allow partial transfers of an item, if the item specification allows it. In this instance, Alice would create two transfer particles, one to Bob for the principal, and another back to herself for the remainder. Similarly, multiple transfer particles may be used to reference many transfer particles owned by Alice and transfer them all to Bob in one execution, thus guaranteeing atomicity and reducing network load. Key elements of the Radix ledger are network nodes, and their main components are Radix engine and Cerberus. The Radix engine is an application layer, which dictates which input or output particle pairs are valid, while Cerberus enforces the atomic commit of updating the state of multiple particles. Atoms must be committed or rejected by Cerberus consensus atomically. Either all particles within the atom are valid and the atom is committed, or one or more particles are not valid and the atom is rejected.